About to start one of the lively sessions of the meeting, and this is going to be the poster flash session. So each poster presenter has about 5 minutes. It can be less than that, but not more than 5 minutes to say a few words about his poster. So these are the poster presenters, and let me remind you that at 8:30 we're going to have the poster session itself. 37 posters. So this is only a taste. So we have 37 posters and beer and snacks. So you are welcome to come and see the posters and discuss. And now we're going to do it quickly, so 5 minutes for each presenter. And let me remind you 2 things. First of all, we're going to have a prize for the best presentation. So one of these guys is going to win a nice prize. And we're going to give 3 prizes to 3 posters. So you prepared your posters, and most of them are very nice, but 3 of them will be given a prize. So this is the order. So please approach. So every time the name will appear, let me show you an example. Okay, so Ronit Kedmi will be after that. Ranit. Sorry. Okay, please.
Okay, you can put it here. Oh, yeah, sure. Okay, maybe this will be convenient. Can I have this one? This will be more convenient for me.
The best thing to do is to use the mouse as a pointer, and then this thing can be videotaped. And okay, please talk to these microphones so we can record you.
So I'll use this one. Yeah. Good evening. I'm Dhruva Rai, working the group of Professor Abraham Nirjan, and my poster is about the circular current in molecular wires. So within the tight binding steady state approach, we studied the following: internal current distribution, that is the local current distribution within the molecular wires, how current will distribute within the molecules. And we studied the effect of dephasing, that is we studied effect of dephasing, that is decoherence, and we also estimated the local magnetic field. So let me go quickly over from the first panel. So as you can see out there, we have here a benzene in meta connection. You can see here the length of arrow is proportional to the current in that particular bond. So here you can see I2 much larger than I. So in some voltage range, the current through this lower branch exceeds the net current I passing through this particular molecular system. So when current I2 exceeds the net current I entering the loop, the current in the other arm, that is the current in the upper arm, must flow in opposite direction for current conservation. So here in this particular example, the current in both branch, upper as well as lower, that means current I1 and I2 both are much larger than current I. In fact, the current becomes maximum at 2 volt, and at 2 volt at that particular voltage, the current I1, the circular current I1, so circular current IC is 18 times the net current I passing through the molecule. Now, interesting thing here is that as you cross the voltage 2.1 volt here, the current change the direction here. So in the range 0 to 2.1 voltage, current is flowing in anti-clockwise direction. Once you cross the voltage 2.1 volt, the current will start flowing in clockwise direction. So similar effect we have found in 2 loops also. These are the 2 loops. More interesting thing here is that you will not find bond current here. You will not find current in this bridging bond, which is common to both loops. Rather, current will flow only in the periphery. Current will flow only in the boundary, and the current is here a circular. Here current IC, it flows only along the boundary. So similarly, here also we found circular current in 3 loops sharing the boundaries. So Now we also studied the effect of decoherence, that is pure dephasing. So we found that as the dephasing rate, maybe you cannot see here, the dephasing rates are given in energy units, 0, 0.01 electron volt, and 0.05 electron volt. So as the pure dephasing increases, the IV characteristic curve of the molecular wire with loops, this kind of, so this IV characteristic curve, it will get smooth. It will become more smooth and smooth. So the step-like characteristics, it will get disappear. We also studied, in fact, we estimated the induced magnetic field at the center of the benzene ring. For instance, here, we found the magnetic field to vary like this. So at this particular voltage, the current will become maximum, and the current, after beyond that, the magnetic field will change the direction. So the magnetic field reaches as high as 0.23 Tesla at 2 volt bias. And so this is the message in the text form, in the red text here. I'll just read literally. Circular currents and the induced magnetic fields as well as dephasing effects should be considered in designing molecular electronic devices. So, and yes, so please make sure to visit the poster, P30, for more details about it. Thank you very much.
Okay, thank you very much. נזכירכם עד 5 דקות.
Okay, I'm from Dan Perleb. Are you worried of losing your hair? The hair follicle is a regenerative organ which undergo repeated cycles of growth, destruction, and a delaying phase. On the transition from the delaying phase to growth, responsible unique cells, which are the hair follicle stem cells. In the male balding, sorry, the hair follicle is stuck in the delaying phase, unable to go through to growth. In our lab, we're specialized in targeted RNAi delivery platforms, which enable us to control gene expression level in specific cell types. In my project, I developed RNAi delivery strategy to target hair follicle stem cells. Okay, with this novel technology, I want to exploit this technology as a new approach to study stem cell biology. Okay, come visit our pastor.
Okay. Our poster is about nano-antenna project with a collaboration between Yael Hanin, Amir Bog, and Kobi Shoyer. We want to construct a nano-antenna for energy harvesting application. It will work in the mid-IR and visible light range, which means it has to be nano in order to capture the light from the sun. So we need an antenna and high-frequency diode, which will take the electromagnetic radiation and excite the nano-antenna with AC radiation. And then in the implemented diode, a high-frequency diode will rectify the AC current into DC electrical power. The milestones are implementing and testing nano antennas in the IR range and visible range, and developing approaches to form a CNT, which is carbon nanotube-based diodes, as you see in the picture, as part of the antenna array system. The carbon nanotube-based diodes we will develop in both RF and IR regimes. And later we integrate the CNT with antenna structures to have the total rectangle. These are some preliminary results. Here you see we have arrays of antennas, and here you see the scan of a whole array, which corresponds to this image. And when the array is broken, of course, the response is much lower. It's 2 orders of magnitude lower for the broken antenna. And in the future, we will place the diode here and hopefully see a higher response and rectification. Here is the first proof of so we tested optically using a Bragg experiment, and in the red, the red is the response of when the light is polarized. If it's a dipole antenna, and when the light is polarized in the X direction, which is the blue line, when it's polarized in the direction of the antenna, you see the high response, the blue line, and when it's perpendicularly polarized, you see that there is almost no response, and this is the simple Bragg response, while this is the resonant antenna response. This is the optical setup, and some HRSM pictures, and you're all welcome to see the poster. Thank you.
Hello, my name is Asaf. I'm working under the supervision of Professor Gil Markovich. And this work was in collaboration with Zahava Barkai. So we have developed a synthesis of hollow silver nanostructures, taking advantage of the nanoscale Kirkendall effect. This effect on its own is very interesting, and it deals with diffusion through solid-state systems. And you should keep in mind that this type of diffusion is nothing like diffusion in a liquid environment. For instance, the very basic concept of motion is described entirely different than motion in liquid systems. And although this process should be heavily controlled by defects in the crystal structure and surface imperfections, we were able to create highly ordered crystal structures, as you can see in the high-resolution TEM images. The reactive template for this process was nanocrystals of silver oxide, which go through a process of photoactivation. These crystals are highly fluorescent, and the fluorescence is enhanced significantly after the creation of the hollow particles. I will try to convince you, if you will come to my poster, that this type of surface enhancement, I believe, is not the regular type of electromagnetic surface enhancement, and there is also a factor of what is called the chemical surface enhancement. We were also able to see some very interesting Raman features enhanced on these particles, like all types of combination bands from molecules absorbed in these particles. So, thank you.
Hello, my name is Ram Dvash. I'm a master student at Dr. Dan Peer's Laboratory of Nanomedicine from Life Science Faculty, Department of Cell Research and Immunology. In our research, we are using carbon nanotubes as a therapeutic agent treating inflammatory bowel diseases, abbreviated IBD. The major types of IBD are Crohn's diseases and ulcerative colitis. These diseases are autoimmune diseases in which the immune system attacks the gastrointestinal tract, causing inflammation. The goal of our research is to examine a novel approach for treating IBD using targeted carbon nanotubes attached to antibodies and other biological molecules such as nucleic acid, RNAi, etc. Leukocytes have a fundamental role in the pathogenesis of IBD. The leukocyte integrin beta-7 contributes both to the recruitment and retention of lymphocytes to the inflamed gut. Here we utilize the monoclonal antibodies raised against the integrin beta-7 as both targeting agent, directing carbon nanotubes to gut leukocytes, and as a blocking agent that will block the adhesion between the leukocytes and the gut epithelial cells, and thus hoping to inhibit inflammatory response. That's all. More details at the poster.
Hello, my name is Amir Chevroni. I'm from the research group of Gil Markovich, and I'm here to present this collaborative project between the Markovich and the Cheskis group. We're working on synthesis of iron oxide nanoparticles at the moment. For that purpose, we have developed a very complicated system which involves a low-pressure combustion chamber. Into the center of the flame that we form, as you can see in the picture here, we inject nebulized precursor solution. We're currently using iron chloride. And you can see it's actually very hard to see in this slide right here, the little column of particles that forms right underneath. The result is highly crystalline nanoparticles of spherical morphology. You can see they're highly crystalline from the diffraction images. In parallel, I've also attempted to develop an alternative method in which I take an inert substrate such as silicon, and I dry out the precursor solution right on it and expose it to the flame front for a few minutes. And the result is actually much smaller particles for the order of 20 to 50 nanometers as opposed to these. These are quite large. They're like 500 nanometers. And these are not only smaller, but also thinner. They tend to form perhaps sheet-like morphology, I don't know. And they're also highly crystalline as the rest. You're welcome to see the details in my poster. It's poster number 20. Thank you very much.
Hi, I'm Noa. I'm a PhD student at Dan Perez's lab, and my research is focusing on manipulating hematopoietic stem cells targeted by targeted nanoparticles and trapping RNAi. Hematopoietic stem cells are rare cells that can give rise to over 1 billion new blood cells every day, including red and white blood cells. They reside in a special niche called the bone marrow niche that influences the cell cycle. Hematopoietic stem cells are extremely important in bone marrow transplantation, since by entering the cell cycle and differentiating, they can reconstitute all the recipient hematopoietic system. Our lab is developing a new nanotechnology to target and genetically manipulate hematopoietic stem cells using RNAi. With this technology, we hope to understand better and control hematopoietic stem cells' unique cell cycle pattern. For more details, please come visit our poster.
Hi, I'm Moshe. I'm from a low temperature physics group. My poster presents two-dimensional electron gas at oxide interfaces. What we do in our lab is we put two materials, two ceramics, one on top of each other by a pulse laser deposition. And these two ceramics are insulators in their bulk nature. However, when you put them together, the interface is conducting, and there is a two-dimensional electron gas that it's formed. This gas is actually, okay, The gas is actually confined here at the interface in about a few nanometers. So therefore, it is interesting for all the semiconductors industries. What you see here in the images, this is a TEM image taken in TAU. You can see this interface. This is the upper ceramics. This is the lower one. And we actually can decide what is the thickness of the material that we want to grow. We can actually decide during the deposition how thick we want the layer to be in terms of unit cells. So we can do a deposition of 1 unit cell, 2 unit cells, and so on. This is how the surface looks like. It's atomically flat. And all the conduction properties are related to the interface itself, since, as I said, the bulk materials are insulators. In addition, this interface is also superconducting. It's not only conducting. You can see it here on this plot. The conductance goes to 0. And what is unique about this superconductor is that we can control the TC while we apply a gate voltage. So we can go through all of the phase diagram and change TC by applying gate. This is quite unique for superconductors. In addition, if you want to know more about it, what we saw is that we can also tune the spin orbit mechanism in the interface by this gate voltage, and this is also an important feature for semiconductors industry. So you are welcome to see us.
Hi. My name is Rakefet, and I'm from Professor Yossi Shacham's group. The name of the poster is Polymeric Microtechnologies for Electrodes, Actuators, and Sensors. We believe that we are in the beginning of a new era, the era of organic electronics or polymeric electronics. The polymers are all around us. And in our research, we wanted to integrate the substrates and that are polymers, and also the polymers as conductors. For example, in implantable electrodes, the conventional electrodes of conventional materials such as silicon cause acute damage to the tissue. And by using polymers that have a lower toughness than the silicon, we can lessen this damage. For example, in this application, the flexible folded cuff electrode, it was quite famous. Yossi was interviewed on television. There is this robotic hand. It's called the Smart Hand Project. The electrode is around the nerve and connected to a robotic hand that was already implanted in one patient, and a handicap that doesn't have the hand, and the nerve still works. So the electrode that we manufacture is connected to the robotic hand, and that's how we can use his hand to do everything. So the electrode, we developed a photolithography process. The electrode is very thin. It's polymer such as SU8 or polyimide, and 30, 40 microns, and it's thin and can be folded. That, of course, cannot be done in silicon, and that's one way to do it. And the next step that we want to do is to use, we already deposited polypyrrole, a conductive polymer, on this flexible electrode. The polypyrrole is very rough. It increases the area of the electrode, increases the sensitivity, and it also has a very good affinity to the neurons. So that's increasing the sensitivity even more. Another application that we use, and have to be short, is a MEMS actuator, a flexible micromotor What you see here is a PDMS substrate with a seed layer of copper and then polypyrrole again, electrodeposited on it. It's more challenging to do electroplating on copper. In the next slide, I'll show a little bit more about it. Another application is biosensors on a polymeric chip. Here, it's a polyimide substrate, a gold seed layer, and a polypyrrole on this working electrode. And another application that I'll tell you more about it if you come to see the poster is an implantable penetrating electrode that is for implanted in the brain. And of course, the silicon is, we can see that electrodes made of silicon that are implanted in the brain, in the rat brain, in this application, cause very severe damage. It can be seen in histology afterwards, that it cuts the brain like a knife. Not very nice. When we make the electrode out of a polymer, such as polyimide, the damage is much, much less. Here is the electro-deposited polypyrrole on this actuator device. The device is one of the applications that can be used. It's for implanting in the stomach. It's part of a BMP consortium. And here you can see the probes for actuation. Here it's copper, and here you can see the electroplated copper on the PDMS. Here in the same place, it's a polypyrrole. It's a little bit mismatching in the photolithography, but the electroplating of the polypyrrole is even less sophisticated than that of the copper, and it has many advantages, as, for example, the affinity to the neurons and so on. Here also the polypyrrole is electroplated on the copper seed layer. Another application is an environmental water toxicity detection, a biosensor on a polymeric chip. When this is a biochip, electrochemical biochip, and when the נגמר זמן? Okay, so come and see the poster and I'll tell you more about it.
כן? ננופלקס? אוקיי, בסדר.
Good evening, my name is Yulia. Hyaluronan and Itay Diamant are my supervisors. And there was a picture supposed to be video on. Okay. And this work is about colloidal particles trapped in a vortex by laser beam, so that they are forced to move in a circle with constant velocity. No, they're supposed to be circling here. Okay. So this is a non-equilibrium system. And we were interested to study the dynamics and the diffusive behavior of the system. In experiment, we saw that particles... No. Okay. No, not the bottom. Okay. And so in experiment, we saw that particles tend to pair, and it was proved in simulations. So we built this analytical model based on hydrodynamic interactions,
and we could get the theoretical mean velocities and to compare them with simulation velocities and experimental velocities. This is a no-fitting parameter graph and one fitting parameter graph. Okay, and this is diffusion. This is log-log plot of mean square displacement versus time. You can see the crossover from single-file subdiffusion to normal collective diffusion. Okay, this is it. Please come to see it. Thank you.
Okay. Slideshow.
Thanks. Hi everybody, I'm Kobe, and let me tell you a bit about what I did with Ron Lifshitz and Itay Diamant from physics and chemistry in Tel Aviv. So let me start by telling you something about soft matter quasicrystals, something which I'm sure most of you know nothing about. So I'll start with the experimental discovery. About 6 years ago, this group of people discovered that if they take a specific type of dendrimers, this type, in a solution, these dendrimers assume a conical shape. Now, these conical molecules, right, they self-assemble into micelles. Now, most of you know about these type of micelles, but what this group discovered, and it gave them a Nature article, so we advise it is important, is that these nanometer micelles self-assemble into complex structures. One of them is not a crystal, but a quasicrystal. Now, at this point, you are wondering, what is the difference between a crystal and a quasicrystal? Well, as the name may infer, a quasicrystal is not exactly a crystal as you know it. You know of periodic crystal, that is, crystal that is repeating itself in real space, okay? Quasicrystal is not periodic at all. And, okay, let me move on quickly to the next nice thing about these quasicrystals. They have 12-fold symmetry. And what is 12-fold symmetry? Pretty simple. If you turn the sample 30 degrees, you'll get essentially the same thing. Now, this is impossible in regular crystals. This is the so-called forbidden symmetries. So this is all pretty nice. Again, they got Nature. But why is this happening? How can we explain this? Why didn't they get just the regular liquid crystals as everybody else? Well, then, that's what we did. We are offering a theoretical model, and the insight for it comes from a very different hydrodynamical system, which I don't have time to describe now, but I can describe if you come to my poster. And so I won't tell you about the insight, but let me just tell you that what we did is to replace this micelle with a simple model of a soft core and some repulsive corona around it. And also, in this case, as you can see here, a van der Waals attraction between soft cores, but that is not essential to our model. We went from the microscopic description to the macroscopic description. That is, we started from a description of one micelle. Then we wrote a theory explaining the entire system. To say, we wrote down the energy, the free energy of the system. So I can't go into the details now, but I will go into the details later. And if you ask me, I will explain you what's the trick we used to get these very nice results. So one of them is just a regular crystal, right? You all know this. So this is what they also got in the experiment. We can also achieve an hexagonal crystal. That is only by changing the temperature in our model. And the nice thing, And what makes this model so success is that we also got a quasicrystal in the model. So you can see a 12-fold symmetry, exactly the same symmetry as they got in the experiment. There are also new experiments with different molecules, all having the same symmetry, which makes this very interesting and possibly our model very generic. And with these very nice images, I will end and tell you all, thank you very much for listening. Please come to see my poster. Thank you.
Hello, my name is Itay. I work under the supervision of Dr. Yoram Dagan in the physics department. I will show our work on the doping-dependent bosonic modes in the high-temperature superconductors. It doesn't really interest you, but let's see. Okay. So, maybe you know, maybe you don't, about the superconductors, and it's known that for regular superconductors, the mechanism behind this is the electrons are paired into Cooper pairs, and this is done by phonons. This was found by Gaver and Macmillan and Rowell. They saw some interesting features at relatively high energy, and they fit this data and found that the mechanism behind the electron pairing is phonons. And for that, they got their Nobel Prize. BCS is Bardeen, Cooper, and Schiffer, and Guyver. And about 25 years ago, high-temperature superconductors were found. And today, there is still no conclusive evidence for the coupling mechanism in these high-temperature superconductors. And we believe we found the answer. So we made the point contact spectroscopy in which a small nano-sized tip slowly approaches a sample, a thin film, and this is our results. And since these conductants show roughly the same features that was observed by Rowell and Macmillan, and since these results are doping dependent, we believe that our results show that the high temperature superconducting pairing is done by spin excitation. And we believe that we solved this problem. Thank you. Okay.
Hi, I'm Shoshi. I'm a PhD student at Dan Pearl's lab. Oh, okay. No. So that's the end. Ah, okay, that's it. לא, אבל זה לא אני.
לא, כי עשית אחורה. תעשי על העכבר.
זה מה שעשית קודם. So I'm Joshi, I'm a PhD student at Dan Pearl's lab. I will be focusing on investigating the molecular mechanism of hyaluronan-coated nanoparticles, both in blood cancers and inflammation. Hyaluronan, HA, is an extracellular and cell surface associated polysaccharide. It is composed of repeating units of disaccharides, N-acetyl-glucosamine, and D-glucuronic acid. HA participates in joint lubrication, holding together connective tissues, but also in embryonic development, tumor development, inflammation, and tissue repair. HA exerts different biological effects depending on its molecular size. And here, literature reports regarding these effects are not consistent. Our goals, so as I said, are to investigate the molecular mechanism of HA-coated nanoparticles in inflammation and blood cancers. Doing so, we would be able to tailor the appropriate carrier for a specific disease and ultimately to establish a personalized medicine approach. So in order to do so, we're planning to create a set of nanocarriers distinguished only by the length of their anchored HA. This would be done by an enzymatic cleavage of HA, size fractionation of the obtained fragments, and attachment of them to neutral liposomes. For more details, you're very welcome to visit our poster. Thank you very much.
Okay, thank you very much for listening and for participating. And we're going to have dinner now. And מה לעשות? ארוחת ערב? ב-7:30. At 7:30, so you have some free time. And don't forget